All right, section 7.4 is estimating a population standard deviation or variance. I'm going to kind of summarize what we've looked at so far in chapter 7. We have our population parameters that we're trying to estimate by using our sample statistics. And we started with our population parameter P, and we used P hat as our single best point estimate. We then moved on to estimating the mean using X bar as our point estimate. What we're going to look at now is estimating our standard deviation by using a sample statistic S. Remember, the population variance is sigma squared, and we're going to use S squared as our sample statistic for that. This section we introduced the chi-squared probability distribution so that we can construct confidence interval estimates of a population standard deviation or variance. We also present a method for determining the sample size required to estimate a population standard deviation or variance. We're going to look at a new distribution. We've already looked at the standard normal distribution, a regular normal distribution with parameters mu and sigma, the mean and the standard deviation. And then we looked at a t-distribution that we used when estimating a population mean when the standard deviation was unknown. Now we're going to learn a new distribution, and that's called the chi-squared distribution. In a normally distributed population with a variance of sigma square, assume that we randomly select independent samples of size n, and for each sample compute the sample variance S squared, which is the square of the sample standard deviation. The sample statistic chi-squared has a sampling distribution called the chi-square distribution. This is the test statistic for the chi-square distribution. This is the Greek letter chi, so that's why this is called chi-square. N minus 1 is the degrees of freedom, just like with the student's t. S squared is your sample standard deviation, and sigma squared is your population standard deviation. So it's a ratio between the sample standard deviation and the population standard deviation. Properties of the distribution of the chi-square statistic. First of all, it's not symmetric. We would say this distribution is skewed how? Left or right? It's skewed right because remember the tail tells the tale. There are no negative values here from the chi-square. Well, that makes sense because in the chi-squared distribution, everything's squared or positive. As the degrees of freedom increases, our distribution, though, does become more normal. Here's a sample with degrees of freedom of 10, one with the degrees of freedom of 20. So the chi-square values will be 0 or positive, but it cannot be negative. And the chi-square distribution is different for each number of degrees of freedom, which is found by taking the sample size minus 1. As the number of degrees of freedom increases, the chi-square distribution approaches a normal distribution. In Table A4, each critical value of chi-square corresponds to an area given in the top row of the table, and that area represents the cumulative area located to the right of the critical value. Now, this is different from the other distributions. If we look at a chi-square distribution, notice it says this is the area to the right of the critical value. When we did the normal and the t-distributions, we were looking at an area to the left of the critical value. So this is different. Pay attention. When we read this table, we see the degrees of freedom that are going down the side, and then up at the top, we have areas to the right of our critical value. So for example, a simple random sample of 22 IQ scores is obtained. Construction of a confidence interval for the population standard deviation requires the left and right critical values of chi-square corresponding to a confidence level of 95% and a sample size of n equals 22. The instructions here are to find the critical values corresponding to a 95% level of confidence. So what we would want to do is we'd find the critical value or the chi-squared for the left, and that area, because it's a 95% level of confidence, this area in between is going to be 95%. So that 5% has to be equally distributed to both the left and the right. We do not have symmetry about 0 here, so there's not going to be any relationship here between these numbers other than the left-hand bound is going to be smaller than the right-hand bound. So let's go back to our table and look up the degrees of freedom of 21. Our sample size, remember, was 22. Let's go to the chi-square table and see if we can find degrees of freedom of 22. We can. That's this blue line right here. And this is where I'm kind of at a disadvantage here because I've got the row. I need to look and pay attention to what columns I need. If the area to the right is 0.975. That's going to give us our left-hand bound because this is giving us the area to the right. 0.975 would be to the right of our left-hand bound. The area to the right of this number is 0.975. And the area to the right of this number is 0.025. So let's go back to this table. And that means that we're going to be looking at this column here, the third one over, and this column here for our right-hand bound next to the last, it looks like here. So we go down to 22, and we see our left-hand bound is 10.982. Our right-hand bound is 36.781. We use 21. The sample size is 22. We use 21 degrees of freedom. Our left-hand bound is 10.283, and our right-hand bound is 35.479. 10.283 and 35.479. So estimators for the variance. The sample variance S squared is the best point estimate for the population variance. The sample standard deviation S is a commonly used point estimate for sigma, even though it's a biased estimate. This one is unbiased. Remember when we talked about bias, but the standard deviation is biased. So for the confidence interval for estimating a population standard deviation or variance, we've gone over these variables before. Chi-squared sub L is our left-tailed critical value for this chi-square distribution. Chi-square sub R is our right-tailed critical value for the chi-squared distribution. The requirements here is first that we have to have a simple random sample, and the second requirement is that the population must have normally distributed values even if the sample is large. This one, the chi-squared test, we've really got to check the distribution. You may have to do a normal quantile plot for your data to make sure that you have normality. The confidence interval for estimating a population standard deviation or variance is given by this formula. This is for the variance. Confidence interval for the standard deviation would just be the square root of that. So if you can find your chi-squares, now why did we go from left to right being on the correct side? We had chi-squared sub L over here and chi-square sub R over here. Why did we switch them over here when we set up the inequalities? Well, this number is bigger than this number, isn't it? What happens when you divide a number by a bigger number? The numerators are the same here. It gets smaller. That's why we have to do the chi-squared sub R on the left and the chi-square sub L on the right for our critical values. For constructing a confidence interval, then, we're going to follow these steps and then evaluate the upper and lower confidence interval limits. Now, on your TI graphing calculators, we do not have a distribution for coming up with these critical values. If a confidence interval estimate of chi-squared is desired, take the square root of the upper and lower confidence intervals and change the sigma squared to a sigma. Round the resulting confidence level limits. If using the original set of data to construct the confidence interval, round the confidence interval limits to one more decimal place. That's if you have the original set of data that is used for the original set of data. If using the sample standard deviation or variance, round the confidence interval limits to the same number of decimal places. So that's your rounding rule for these. Caution, confidence intervals can be used informally to compare the variation in different data sets, but the overlapping of confidence intervals should not be used for making formal and final conclusions about equality of variances or standard deviations. So here's an example. It says a group of 22 subjects took an IQ test during part of a study. The subjects had a standard deviation IQ score of 14.3. This is the standard deviation. So that means S is equal to 14.3. Here we're asked to construct a 95% confidence interval estimate of sigma, then the standard deviation of the population from which the sample was obtained. First, we have to verify that the requirements are met. Unless you were provided this, you wouldn't know what the distribution was. So the following display shows a histogram of the data, and the normality assumption can be reasonably met. Seems reasonable, unimodal, symmetric. I would be a little leery because of that gap right there, but if the author says it's okay, we're going to go with that. It's clearly not skewed. N equals 22, that's our sample size. The degrees of freedom then would be 21. We're going to use the table to find the left-hand limit, or what level of confidence? 95. So we go to our z-scores, we're going to use 21 since our sample size was 22. So that gives us 10.283 for our left bound. And the right bound is going to be over here, 35.479. Remember, we already checked to make sure that the areas to the right were correct for a 95% level of confidence. 35.479. We're going to use our calculators now to figure out what the lower limit is here for the variance, and then we're going to find the upper and lower limits for the standard deviation. We were told that the standard deviation is 14.3. So this number right here is 14.3. So we go to our calculators, and for the first number we're going to have 21 times 14.3 squared divided by which one of these two numbers? 0.479. And then the next one, we're going to change the denominator to 10.283. Second enter brings back the last thing that you typed in so that you can just type over it. 10.283. And that'll give us our lower bound and our upper bound. How many decimal places do I round to? Our summary statistics were measured to 1 decimal place. So because our summaries and all, we didn't have the original data. If you have the list of original data, you round to 1 place more than the original data. What we have are the summary statistics, so we're going to round to the same value. So that's 1 decimal place. So this would be 121.0 and 417.6. Now, that's the confidence interval for the variance. What if I wanted the confidence interval for the standard deviation? What would I do? Just take the square root of those numbers. So this would be 11 is less than, sigma is less than, what's the square root of 417.6?